Why is it that when the two waves collide, whether they're constructive or destructive, the two waves still just pass right through each other? That has to deal with something called superposition. We're going to define superposition as when two or more waves, I'll write this down, when two or more waves collide, the displacement of the medium equals the sum of the two displacements. Equals the sum of the two displacements of the individual waves. This is the superposition principle. When two or more waves collide, the displacement of the medium equals the sum of the two displacements of the individual waves. What does that mean? It means if I take two waves and I slam them into each other, wave number one might have this height, wave number two might have that height. When they collide, it's just the two heights added together, and then they'll just pass right through each other. Basically what it's saying is that the two waves don't interact, they just pass right through each other, they don't disturb each other. Now, this seems a little counterintuitive, but if you think about it for a moment, you realize that it has to be true. If you've ever been in a room with lots of people talking at the same time, you know that sound waves, at the very least, have to be able to travel through each other. You can talk to your friend across the table, even though there are other sound waves from other people that are bouncing in and passing through your own wave. If this didn't work, talking in a room with lots of people would just be a jumbled mess of sound that bounced every which way, and you could never be able to make out any of it. We can use the principle of superposition to describe two phenomena, namely constructive and destructive interference. So constructive and destructive interference are what happens when we have multiple waves combining together to either add up or cancel each other out. So say I have a speaker emitting some sound wave. The sound wave is traveling along. It has a profile that looks like this. Let's consider a second wave. The second wave matches up exactly with the first wave, but the second wave comes from a speaker that's a little bit behind the first speaker. The two speakers are displaced by a certain amount, by a certain distance. In this case, I've drawn it as a one-pole wavelength. I'll call that lambda. If that's the case, then what we get is called constructive interference. You can see these two waves match up exactly. If that's the case, whenever the red wave is going up, the white one is going up as well. Whenever the red wave is going down, the white one is going down as well. So they match up, and they're going to enhance, one is going to enhance the effect of the other. Because they're working constructively together to give you a bigger wave, so the total wave would be the sum of these two waves, we call that constructive interference. And constructive interference happens whenever you have an integer multiple of wavelengths. Once I've been displaced by n wavelengths, where n is an integer, I'm always going to line up again. So this happens if I call this distance delta x, which is the path length difference between the two waves. This happens when delta x equals n, some integer, times lambda. Now we can consider a second case, very similar to the first, except now, instead of having the red go up whenever the white goes up and red go down whenever the white goes down, what I'm going to do is have red go up, pointing up when the white one goes down, and red go down when the white is pointing up. Here we go. Now you can see here my two waves are displaced by only half of a wavelength. It only goes up once. So here, the distance between the two speakers is half of a wavelength. Okay, again, we can call that distance x. Now what's going to happen? When I combine those two waves, whenever the red's going up, white's going down. Whenever the white's going up, the red's going down. One's positive, one's negative, they're always going to exactly cancel out. Because they're always canceling out, we call this destructive interference, which happens whenever I have a half integer multiple of wavelength. So whenever the distance between the two speakers is n plus 1/2, where again, n is just some integer, n plus 1/2 times the wavelength. So it goes a full number of wavelengths and then just shifts by half of a wavelength. So we would say they're 180 degrees out of phase. Whenever that happens, we get destructive interference where the two waves are going to cancel each other out. In summary, when the path length difference, that's the distance that the wave travels, or in this case, the distance between the two speakers, when that is equal to some integer times wavelength, so again, n is any integer, 0 plus or minus 1 plus or minus 2, dot, 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 then you get constructive interference. However, you will get destructive interference if that same quantity is equal to n plus 1/2 of the wavelength, where again, n is just some integer. So here, we're multiplying by n plus 1/2, here we're multiplying by n. Just that small difference, it gives you the difference between constructive and destructive interference. We can consider interference in 2 dimensions as well. So here, let's say I have a source of circular waves. So it could be I have some pool of water and I'm just dipping my finger in at a constant frequency, so that we are emitting circular waves that are coming out. So every time I dip my finger in the pool, that emits a circular wave of water, and the circular waves spread out, going further and further in different directions. Now the way I've drawn this here is kind of peculiar. We're going to map this to different, to what the wave is actually going to look like. How high from the baseline is the wave. I'm going to say points on the line represent peaks in the wave. Call this point 1. And points between lines, call this point 2, represent valleys. So if I were to cut the wave in half and look at it from the side, what you would see is something like this. And point 1 would be on the peak of the wave. And I go to another peak, here's my next peak. And then point 2 is in the valley, so that would be right there. Okay, so this is how my 2-dimensional waves are going to be, this is how we're going to draw our 2-dimensional waves. Diffraction is the spreading out of a wave as it passes through a boundary. So for example, say I have a wall with some hole in it. We send some waves in towards this wall. Here are some peaks in the wave. The wave is coming this way towards the hole in the wall. As the wave passes through the wall, it's not going to act just like a ball where it just comes through and stays straight. The wave will actually spread out. Spread out in different directions. And in doing so, the wave will reach further out to the sides. And that's, this is one of the reasons why, if I can't see you, if I'm on the other side of a door, I can still hear the sound that you're making through a doorway. Because even if I'm standing over here, the sound wave coming from your voice is going to spread out and still hit my ears. The spreading out of the wave as it passes by different boundaries is called diffraction. Now, we have a small demonstration we can do with this. We're going to do it with light waves with a small aperture that we're going to shine a laser through. So I have here a very simple setup. I have a laser pointer here. I've got a small aperture here. I'm going to slide the aperture forward in front of the laser pointer. And we're going to see what happens when I try to pass the laser through a small slit in my aperture. Here is my laser pointer dot. We're going to see what happens when I try to close the slit so that the light wave is forced to pass through a small vertical hole. Here we go. I'm closing the slit. You can see my laser is starting to spread out horizontally when I have a vertical hole, a vertical slit in the wall. Let me try to align this just a little bit better. Oops. There you go. That's a good line. You can see as soon as I try to align my vertical slit, I get this horizontal spreading out of the light wave. And what's even more intriguing is you can see I've got individual dots in my light wave. I've got a big bright one in the middle there, and then these secondary ones off to the side. Why do I get those different dots? And I can change their size just by changing the size of the hole. Why do I get those different dots when I shine the laser through an aperture? Now let's consider interference between two sources of waves spreading out as circular waves in 2 dimensions. Let's look at different points here. I'm going to consider a couple of points. I'm going to consider this, we'll call that point 1. I'll call this point 2. And I'll call this, let's see, right here, we'll call that point 3. Let's see what's going on. Am I getting constructive or destructive interference at those different points? Well, at point 1, I can see I'm on the line for the waves coming from source A, which should mean that I'm at a peak in the wave. Similarly, I'm on the line for waves coming from source B, so that should also be a peak. So I have 2 peaks in my waves coming from source A and source B, which means I should be interfering constructively right at that point. If I'm interfering constructively and they're both peaks, I should have a very big peak in the wave at point 1. Let's consider point 2. Well, for point 2, I'm right between 2 waves coming out of source A. I'm between the 2 peaks of the wave coming out of source A. However, I'm right on the peak of a wave coming out of source B. Coming from source B, I'm on the peak. Coming from source A, I'm between peaks. That means I'm in the valley of the wave from source A, but I'm in the peak of the wave from source B. So this would mean I'm interfering destructively at point 2. So point 1 is constructive. Point 2 is a destructive type of interference. What about point 3? Here we go. I am between two peaks of the wave, so I'm in a valley from source A. Similarly, I'm between two waves of source B at point 3, so that's another valley. Now you might think those are both going down, so maybe it should be destructive. But if the waves are both going down, that means I get an extra deep valley, which is still constructive interference because they're adding together and making a bigger valley than I would have had otherwise. Let's see what happens when we shine light through two slits. These are two vertical slits that my laser beam is shining through. Let's turn that on. What we can see, we have lots of little dots there. And in fact, we have a big region of green dots right in the middle here, and then teeny tiny little dots all along there. Then it gets a little bit darker, then a bunch of bright spots again, bunch of bright spots on this side, teeny tiny little dots interspersed by big regions of brightness on either side. So why is that? So we have a wall with two holes in it. Call this hole 1, call that hole 2. We've got some screen over here, and in principle we are going to have, based on that screen, we're going to get a bright spot in the middle, and then spots equidistant on each side. I'm going to label each spot with a number. We call the middle one, I'll call that 0. And then +1, +2 on one side, -1, -2, etc., etc. I'm going to label the distance between the holes. I'm going to call that D. Now, the question is, how do I get constructive interference? Well, we know, let's take the n equals +2 dot. From hole 1, that wave has to travel a distance we'll call R1. From hole 2, it's going to travel a distance that I will call R2. Now we know that the path length difference, delta R, which is R1 minus R2, to get constructive interference, has to be some integer multiple of wavelengths, which I will call m. Conveniently, the same n as the number of my dots. That's what the m means. It's how many wavelengths do these two waves get separated by. Okay, well, what's the difference in the length of those two lines? Well, it turns out there's a fairly long derivation you can do for that. It's not hard, it just involves Pythagorean theorem. But we're going to end up with an approximate form that's going to be fairly good, provided that the distance to the wall, which I will call L, the distance between the two-slit grating and the wall, is very, very large. If L is large, we can make a very simplified approximation. Because at that point, these two lines are going to be almost parallel. The wall is very, very far away, and this distance D is very, very small compared to that distance L. The lines are going to be moving pretty much straight. In that event, what we can say is that we consider a different line here. A line to the dot from the center of my aperture, the center of my two slits. I'm going to call that angle theta. Well, if that's the case, what we can do is we can identify a similar triangle to this red triangle. That triangle is right here. we're making an approximation. These have to be very explicit in that. We are making an approximation here, but in my approximation, I'll draw this in white just so we can see it better. My purple triangle right there has an angle theta here. D is still the distance between the slits. But then this side is my path length difference. By geometry, we can see that this has to be d sine theta, just by SOHCAHTOA. If that's d sine theta, then what that tells me is that d sine theta has got to be m lambda to get constructive interference. So, in order to get the bright green dots, the light waves need to interfere constructively. If they're interfering constructively, d sine theta has to equal an integer multiple of wavelengths. So we can say d sine theta equals m lambda, where m is just -2, -1, 0, +1, +2, etc., etc. Any positive or negative or zero integer. D is the distance between the slits. Lambda is just the wavelength of light that we're shining through. Each slit has its own geometry, and we could do a derivation for each case of the geometry. But it turns out that while the math might be a little bit different, the principle is the same. It's all just constructive and destructive interference. Where are my waves adding up and combining constructively? Where are they canceling out and combining destructively? It's the only thing that's going on. It's just different complicated geometries. Now let's see what happens when I shine my laser light through a bunch of slits. So this is going to be laser light through multiple vertical slits. So a whole bunch in a row. Let's see if we can put this up. Move this off to the side. There we go. We can see, we can zoom in on that we get, once again, a bunch of tiny small dots on the side, separated by regions of brightness, alternating regions of brightness and darkness. I'll try to focus that a little bit better. There we go. Again, we see regions of small dots and then kind of big bright regions separated by dark spots in the middle. Here's what happens when you shine laser light on a bunch of holes arranged into a square grid, much like a crystal. You can see again, I get individual little dots around here, but then I get these concentric rings that are forming around the center. So I have regions of alternating bright spot in the middle, then a dark region, then another bright region of dots arranged in a square, dark region, bright region, dark region, these alternating rings of concentric circles. So we can do diffraction basically by shining light through different shapes, different holes in an aperture. So there are some common hole shapes that show up pretty frequently, pretty regularly, so we want to go over where the constructive or destructive interference peaks appear for these types of holes. So the first one we just derived, that's two-slit diffraction. And we showed that if I look at D, which is the distance between the slits, times the sine of the angle going to the bright spot, we get d sine theta equals m lambda. And this is for constructive interference peaks because it goes to the bright spot. Remember, m is just any integer, positive, negative, 0, doesn't matter. It turns out that if you do the exact same derivation for many slits, you get the same thing. You get constructive interference when d sine theta equals m lambda, where here d is the distance between any two of the holes that are in the many slits. This is also called the diffraction gradient. So if I have many lines in a row, I'll get d sine theta equals n lambda. Constructive interference peaks looks exactly like two-slit diffraction. Single slit's a little bit interesting. You might ask, how do we get interference from a single slit? That derivation is a little hard, and it's a little hard to see intuitively because you think, well, there's not multiple waves coming in. But there is in this sense. If I look at any single slit, it's got some width to it. That width has multiple different waves that are coming through it because it's not just a single point where there's only one wave that can come through. I can line up a bunch of different waves along the width. And even in that case, you will still get interference. This time, the equation looks very similar. D sine theta equals m lambda, but there's some subtle differences. One of the differences is that d is no longer the distance between slits, of course, because I only have one slit. D is instead the width of the slit. So if the width of the slit is d, there could be, maybe the slit is 3 microns wide. If it's 3 microns wide, I just plug in that width for d. Sine theta is still the same. Theta is just the angle to the peaks, except now we're looking at destructive interference. So we're looking at, not the peaks, we're looking at the valleys, the places where the light cancels out, where it destructively interferes with itself. Those destructive interference peaks occur again at m lambda, where m, again, subtle difference here, can be plus or minus 1, plus or minus 2, plus or minus dot dot dot, any positive or negative integer, but not 0. This is a standard, these are kind of the standard ones that show up pretty frequently. But we could do this with any diffraction interference, we could do with any geometric shape. We did it with helices before. We could do it with any shape I want. I could make it a cross, I could make it a rectangle, I could make it a pentagon. Doesn't matter the shape. What matters, however, the only thing that really matters is that is this basic principle. I look at the light waves that are coming through. The path that the light takes is going different distances. If the distances are different by an integer multiple of wavelengths, they're going to constructively interfere because the waves are going to add up at the same time. If I look for places where I get dark spots, we're getting destructive interference. Those are places where half of the waves are going up and half of the waves are going down, so they exactly cancel out. So why are we so concerned with diffraction and interference? Well, there's a lot of different reasons. Suppose you're an engineer, you're dealing with sound waves, acoustics. Diffraction and interference obviously plays a big role there. For somebody like myself, I am somebody who's very interested in nanotechnology. I work a lot with chemists and biologists trying to build different structures on a nanometer level. So I want to know, how can I actually look at things at that size scale, things that are much too small to see. And there's generally 3 techniques that you can use to look at things on a nanometer level. So we could use microscopy. Now the problem is that optical microscopy, microscopes that use just regular old visible light, can't actually see that small. You are restricted to seeing things that are about the same size as the wavelength or bigger that you're dealing with. So visible light has wavelengths from 400 nanometers to 700 nanometers, which means about the smallest thing that I can resolve is 400 nanometers. It's kind of a fundamental limit. I'm not going to be able to see things like DNA and proteins, which can be much smaller than that, hundreds of times smaller than that. So microscopy is basically out unless I have an electron microscope or possibly an atomic force microscope. The other option is scattering. So the way scattering works, this is usually for dealing with things that are even smaller than that. But basically, this is how they discovered the size of the nucleus. This is how they discovered the fact that there was a nucleus. Was I send subatomic particles into some sample. I fire them in very, very fast. And I just look for how the subatomic particles deflect. So it's kind of like trying to find out the shape of something by throwing baseballs at it and then seeing where the baseballs bounce off of it. The problem is that scattering is usually not very good for dealing with nanometer-sized things either. The third technique is to use diffraction. So if we were back in the early 20th century and we had just discovered X-rays, we would know that the wavelength of X-rays was about the same size as the spacing of atoms in a crystal. So we could use X-rays, we could shine X-rays onto some sample. So let's say this is my surface. I shine a bunch of X-rays in. And if my source for X-rays is a good source, what will happen is we will reflect off of these atoms and get different spots of constructive interference and destructive interference. And by measuring the diffraction pattern, the interference pattern that arises by shining on these atoms, we can determine what the atomic structure is. It's kind of amazing that even in the early 20th century, physicists and chemists were able to figure out atomic structures well before they had electron microscopes or any sort of atomic force microscope. Now let's see what happens when we shine laser light through this spring that we just take out of a mechanical pencil. Hitting it with our laser, let's see what the pattern we get. So here's the interference pattern you get when you shine laser light through a helix. You can see we have this characteristic X pattern. This is the first thing that Rosalind Franklin saw when she looked at X-ray diffraction on DNA. She saw a very similar structure with this X pattern, and she had worked out that this must mean that DNA must be some type of helix, much like our spring is a type of helix.